problems look pretty friendly, actually. So hopefully, like, this talk is sort of a attempt at making us not be so afraid and having more confidence for those types of problems. So what I think we'll do that is what I'm just terming algorithm patterns, which are just methods, techniques, whatnot for solving a given problem. And I guess as I started to learn about this myself, one thing that it kind of made me feel like is I've been just thinking about complicated solutions all the time. I actually said this like the other week, and I thought it was a pretty good quote, so I put it up here. But a lot of these patterns are kind of more simple, elegant ideas. There might be a kind of a big, complicated prompt on top of it that obscures the pattern. Maybe it's the prompt that's dealing with boxes at a shipping warehouse or actors in scheduling, but underneath it, it's kind of asking something a little more straightforward. So there's quite a few of these. This list is running a little bit. What I have here, I know it's a little dark, but miscellaneous. But it's sort of my thesis that most of the problems we'll encounter either in interviews or in places like LeetCode can probably fall into one of these categories. And for me at least, taking a kind of top-down approach to covering this material has sort of simplified the challenge. So let's start and dig right into the first pattern, which is the two pointers pattern. The two pointers pattern is an efficient technique for searching for some sort of pair in a sorted array. As a general idea, you would use 2 pointers or 2 indexes, 2 references into that array, and they would represent the first and the last element. You then add those values together. Bit of an asterisk there. By add, it's just kind of like some monoidal operation. You're combining them in some way to match some predicate. It's not necessarily summation. If the results match your predicate, you're done. If it's too high, you decrement the kind of the end pointer, that second one. It's too low, increment the start. So let's kind of take a look at what that looks like in practice. So our first problem for 2 pointers, given a sorted array of ints, return 2 indexes where the sum of the value is equal to n. And here we have 1 through 10, n equals 7, and we're just looking for 1, kind of the first match. In this case, our output would be 0 and 5. So let's actually just jump real quick and take a look at an implementation for that problem.
Just curious, are these slides available?
They can be. I can put them on our Slack in about 5 or 10 minutes. Although the code samples will be available a little later. So here is that clear for everyone? If not, there's a couple of TVs around. So this is Go. If the syntax throws you off, just ask a question about it. First line, var pair int. We're just establishing what our return array of integers is. Then we start by creating our 2 pointers. We have an I and a j. So the way that we're assigning that is I is equal to 0, j is equal to the length of our input nums minus 1. And then we begin to iterate. We can just do one pass through and solve the problem. Our condition here, this says for I does not equal j. Go doesn't have while loops. It has multi-purpose for loops. So you can read this as while I does not equal j. This here is just a helper method that we can ignore for now. And we do our first test. So we take the sum of where those 2 pointers are directing in that array. If it is greater than our target, well, then we present it to a number of different cases. So when we add them up, when we compare it to target, which in this case is 7, it can be greater than, less than, or equivalent to. So given it's a sorted array, if our resulting sum is greater than what we're looking for, what should we maybe do next? I know the code's up there, but maybe someone can tell me. Right, decrement the end. So we have our first pointer pointing at the first position, which gives us that 1. Below the second pointer is pointing at the last position, which gives us the 10. Right, and so we then kind of go back through this process over and over until we find our target. So we can actually take a look at this real quick. Okay, so that helper function from earlier just kind of prints out the position of those 2 pointers relative to that array at each step. So we iterate, I guess, 5 times until we find it. Since we're checking that end first and we're going to decrement our end pointer, we step down from 10 to 9 to 8, finally down to 7. 0 plus 7 equals our target number, and we return. So as we were going through this, we were making that decision of which pointer do we move around. Do we move the start, or do we move the end? Any questions on that one?
So, your array was already sorted to begin with?
Correct.
And are there any duplicates?
In this problem, no, there are no duplicates.
Would it still work with the duplicates?
Target sum pairs, it would work with, yeah, it would. You might have to change, you might have to consider how you maybe increment or decrement. No, it would probably be, no, it would be the same, it should be the same.
The algorithm is trying to decide which end to move to reduce the number of choices. Is that what it's doing?
Oh, that is the wrong file. Let me pull that back up. So alternatively, if we were to think of maybe I guess a brute force solution, we would do a normal for loop, begin at I, and then iterate from there to look for a matching number. And then if we had to find multiples of these, we'd have to keep going.
Mm-hmm.
So we'd end up with 2 nested for loops, which would increase the running time of our solution.
And could you explain how the sum, like, if you're looking for the target 7,
Right.
how does the sum give you that number? Because if you sum 2 numbers, doesn't it give you more than the...
Sure. Well, let's go back to our prompt real quick. So we have, a little slow, just stepping through this. On the first iteration, we're at 1 and 10. That's too high, so we bring it in. We have 1 and 9. Is that too high?
Mm-hmm.
Bring it in. 1 and 8. 1 and 7, 1 and 6. So 1 and 6, we hit the sum of 7, and then we return. The answer?
Oh, okay. I was thinking we were looking for a number, not the sum of the values.
Oh,
Yes.
we're looking for our target sum here.
Yeah.
So any problem with this solution, though?
Just a question. So can the upper pointer move in both directions? I didn't quite see that.
So we're kind of initializing our pointers at the bounds of the structure,
Yeah.
and then we're moving them in respectively. So with the idea being, if you're sorted, since your array is sorted, that the upper sort of bound of the structure you're operating on is where that end pointer is initialized to. So it's not going to get any bigger than 10.
Have
So-
you, oh, sorry.
It's okay.
Go ahead. What were you?
I'm just going to say this problem is a bit simplified since we're not asking you to look for the number, 2000, which would not be found through summation here.
Would you, could you look for a negative number in here?
You probably have to do a little extra accounting, but yeah.
Because if I was looking for a negative 7, I would actually traverse the entire array and not find what I needed, right?
Right, so in that case, this will return false. So in this kind of simplified version, here we're guaranteed that the target number exists. However, it would be sort of trivial to account for that. So this solution does assume that we're going to find it. Otherwise, we're going to return an empty kind of integer list here. And we're going to break out of that once the start pointer and the end pointer meet. Because once they've met, we don't want to add the same number twice, and then when they get past each other, we don't want to do the same addition that we've already done. 3 plus 4 is 4 plus 3.
So if you have a negative number, what indices would you give? Because it's gonna, whatever array is given is telling you where the numbers are. But if you don't have any numbers that give you negative 7, then
Well, it's only important that they're sorted. So if they're sorted from like negative 10 to positive 10, then it's fine. If you're given an array that you're not sure is sorted, then with this solution, you'd want to do a sort on it and then provide it to this iteration pattern.
well, I'm asking, would you give an output of something outside the bounds of that array so that you don't actually pick something from the array?
Well, our output here is the two, so what we're looking for in the target sum pair is like which two indexes yield the sum. So we're gonna have to either find that no indexes yield that sum or a given two do.
I guess like on the, when it returns pair at the end, in the event that I is not equal to j, and it hasn't hit the else in the if statement,
Right.
then you can assume, yeah, it might be like -7 or something. Just out of curiosity, so Golang, it doesn't, it's not like Java where you've initialized the pair to be an array of two, of size 2 with like index of, or with values.
Yeah, so with Go, what we've actually done, we've created a slice, which is a substructure of the array that's resizable within those bounds. So here we would just return an empty int slice or int array.
So like an empty int that would indicate that the value is not found in the array.
Correct, correct. Any other problems with this though?
I think the numbers have to be non-negative.
How come?
Well, if you have them sorted and you start at -100 and go down to -90,
Right.
and then you start again at 1, you go up and now pick a number that would only be satisfied with the positive numbers. With the negative numbers, each time you move in, it's going to get smaller and smaller, but not be what you're looking for.
With the negative numbers each time, well, I guess we're looking for the results of
Well,
the summation
as long as
equal
you
to value.
have an index on a negative number, you're going to say, oh, well, it's smaller than our target sum, right?
Right.
So you'll move your positive numbers this way.
I think
I
problem
think
2 in this is going to answer that question.
Okay.
So the sort of the problem with this solution is there's more than 2 pairs that equal 7. So let's take a look at that. So problem number 2 is to find all pairs that match our target. So if you were telling me how to modify our previous solution to sort of match this, how might we go about it?
Don't break.
Good.
First one. And
That's correct.
probably, if you have no duplicates, just increment I and j when you get a match.
Yeah, I'm pretty sure I'm right.
Yeah, exactly. Or at least one of them, right? So that's correct.
If you were to increment both of them, you might skip something that you need.
As long as you didn't, if you didn't have any duplicates and you wouldn't skip something, in the event that you did have some duplicates, then sure, you might end up skipping. So let's visualize this one. That is the wrong find. Oh, for Pete's sake. Okay, sorry that took forever. All right, so we can visualize finding all of them. So this is just like our first solution. We're finding the values 1 and 6, we found that. So we move in the end twice, we find another set. We find 2 and 5, and then 3 and 4.
So in the first instance, you're just moving the greatest value, if you will, over.
Exactly.
Then once you find a pair, then you start moving both of them.
Right, so in the case of having non-duplicates in your array, then you can sort of choose whichever one to move, and it doesn't matter. You can move both of them. That's the most efficient. You'll save one iteration step. In the case of a duplicate, of an array with duplicates, you'd probably only want to move one of them. Because if you had 2 here and then 2 5s, then you want to make sure to catch that second pair. Unless it was entirely unique pairs, then whatnot. So that's the thing about these patterns, that these aren't like specific solutions. You probably won't see the exact find 2 pairs that sum to. some target number in a Amazon interview or another interview, but you'll find a question that's basically asking you to do that, but just with some slight twist to it.
So let's say you had an array and it said 1, 2, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then all three twos will add with the 5 to give you 7 and give you an array that has the indices. Well, it'll tell you where the first 2, second 2, and the third 2 exist. Is that what it would do?
Let's take a look at that. So let's just run a quick test with that and see how it looks.
So I said I said 3 2s in this case, but 4 2s is okay.
Okay. Let's see what happens. And let's just take that out. Ooh, interesting. We only get, we modified in that case. Ah, I modified the same step. Sorry. Okay, so we find that first case, we find the next case. Oh, interesting. So it does look like we're finding every.
It looks like you didn't stay on one of the indices long enough to say 2 plus 5, 2 plus 5, 2 plus 5.
So in that case, that's because we're moving off of the greater value. So in this case, it's the initial value, the smaller value, that has the duplicates. And our algorithm is saying, hey, let's just come one off the high one,
Oh,
right? So now in a real world scenario, though, we might have to imagine how would we account for duplicates using this pattern as a foundation. Any other questions before we hit problem 3?
so did it or did not give you the,
Oh,
what was the output?
so here was the output. So and it failed because we were the way that we had coded the solution was to decrement the end pointer. But if it's helpful, we can quickly kind of change that handling.
Well, I wanted to see if you could do it 1, 2, 3, 4, 5, 6, 7, 8, 8, 8, 9, 10. And, you know, because you said it would look for the larger, but it would,
Sure.
so.
Well, I guess it depends on like, so what would our target be in that case?
Oh, let's make it 9.
Okay.
Right.
Oh, you know what? We don't have a 0 here, so we're going to hit 8 and 1. How are we testing that? So we are actually moving both. Actually, no, that's a different problem.
I think you'd have to change it if you're dealing with duplicates.
Yeah, I mean, there does absolutely have to be some accounting here. So in this case, we're actually in the find multiple pairs version. We're incrementing the start. But this is good homework.
Yeah.
This is good something fun to look into. It is worth pointing out that this problem can be solved another way by using a kind of a map lookup scheme. I'm not going to dig into that, although it is worth considering.
Can you briefly talk about what a map would be
Right, so essentially, as we iterate through our array, we would build a map where each key is the number in that position, and its value is the index. So as you're iterating through, you can check if your number, if the target minus the value of the number that you're on for that index, if that exists as a key in the array, or if that exists as a key in the map, and if it does, then its value reveals the index of the second pair that you need to find the target sum. That's pretty useful. It's actually useful in the next problem. So this one I actually want to throw to you guys for 5 to 15 minutes.
Yeah, so the previous one, what if like, I mean, the some number is presented in the array itself?
If the target sum is in the array?
Uh-huh.
Okay, so I guess I'd have to ask, like, it's 0 in the array? Because we're still looking for, we're not looking for an individual value, we're looking for two indexes, which their values sum to the target. So we have 7, and we're looking for 7, and we have 7 in the array, but there's no other number in the array of numbers where the numbers are between 1 and 10 that equals 7. If our array was between 0 and 10, then of course 0 and 7 would be our earliest match, as long as we're kind of decrementing our way in.
Unless you have 9 and minus 2.
No, so we have 9 and minus 2, that's true, and I'm sure a bunch of other permutations. So this I want to throw at you guys, probably about 10 minutes or so. This is the hardest problem I'm going to provide tonight. So we can get over this one, and then it's downhill. Given an array of integers, find 3 indexes where the sum equals k. As an example, we have -3, negative numbers, 2, +3, and we have an example output, -1, 3, -2, 0, 2, -2. Feel free to do pseudocode, talk to a neighbor, write real code, whatever suits.
It's definitely sorted.
Yes. Yeah, you don't have to worry about that.
Can you tell us the Lego time you're expecting?
ON.
Typo with the sum?
Sorry?
So is the sum a typo, or is it?
That is a typo.
Okay. There was a typo on a previous one too.
I'm sure there's a few of these.
Understand what you're talking about.
The night is dark and full of typos. Game of Thrones.
Can't be as dark as Game of Thrones.
Not that's the long night.
Couldn't see anything.
I mean, I'm not judging you. I'm not going to compile your code. I think it would be cool to find all of them. I mean, honestly, once you know how to find one of them, then it's only just get obsessed with the rest of them. Yeah, that's sort of the value. So it's the same.
So we can use any number of pointers.
I'm interested to see how you solve it.
Okay. Is Go available for downloading to practice?
Yeah, goes. There's the code.
The language, or do you install anything?
Yeah, use golang.org. So someone pointed out the output here is the values, not the indexes, and that's confusing. So I'm gonna fix that real quick.
useful to output that instead of the indices?
Whatever.
I guess it's just a few steps more.
Yeah, I mean, as you're doing it, it's actually just a choice of what you want to return.
This is an array of arrays.
It is, yeah. But you can return whatever you want. If you want to turn like an array of triples, that's fine. You know, just as long as you're able to find the indexes or their values. I can see it. Not with my glasses, but it's all mush. I don't have a pass yet.
Oh.
But I will.
That might. Actually, yeah. There's a water road thing.
That's kind of weird. I remember that moment last week. Because I was like,
Notice how it displays.
Yeah, that's what it's
I totally forgot.
Yeah. So I'm basically just using Julian for this. It's just going to be basically build up a test case.
How was mine?
Realize.
Are you guys comfortable with that?
Yeah, the less I'm seeing, the better.
Yeah. Understood. I do apologize if I was a dim, just.
I didn't. All good. Thank you. It's all good. Thank you. When in doubt, throw yourself under the bus.
Is it their shirts?
Yeah, the back.
Yeah, small.
No, the medium is a small show. They run very small.
Isn't the long sleeve shirt?
What is it? So
I
if you
don't
start at the
remember.
middle,
Did I give you a long sleeve?
Yeah.
I just grabbed one. That's the tag.
Sometimes I hold it.
you're not going to go back.
She goes that way. Oh, yeah. Well, part of it's just the structure of it. It's like, so it's the go packages and technology that everyone was like, go. Yeah. patterns are a skeptical. No, that's the answer. Figure out how you choose the various
Yeah, if it's straighter,
mission success.
You can just have all of it. I've got my report.
Thank you. Hold on.
I thought that there is a water thing, but it's gated because I don't have a key card.
Yeah. How's everyone doing? Anyone like a few more minutes, or are we good? Good. Perfect answer.
So, the answer output is this.
We'll get going in 1 minute.
So where do you find the stuff? Where does it not work? Oh, right. Still need to. So you have to go one.
I got it off Amazon, but the cell, the Nixon, or
no, so I'm not just going to be looking at here, or it's going to be
I could look.
How many people are calling?
On it. I got the box still. These are like
Yeah. I mean, you can assume this. Sorry?
I looked for it.
It changes everything.
Quite a long time.
There are no gaps.
Right.
For my friends. This was the best company I found.
Yeah, it's like,
Adding value is weird thing.
The value there, so
I have a bunch of these ones. Got a bunch of
All right, and I'll email these problems out like later this evening if you guys want more time to keep going at it. But let's take a look at least my solution for it. So there's one big difference here with the other target sum pairs and this target sum triplet. is we're doing a little extra accounting. We're keeping track of what numbers we've seen. I believe that's pretty much it. And so we iterate through our first pass. We're looking to see if our 2 pointers are pointing at a number where the difference between the target and itself exists as a key in the map. Kind of as we went through before, where we have a map of numbers and then their respective indexes, so we kind of reverse that array. If upon looking that up, we find our meet, then we found our first target sum triplet. Any questions on this concept or pattern?
Let's use an example in the difference. Like in your first pass, or the example that using the array that you had.
Sure. So I believe we're not examining this one as we were before with the other ones, just because of the extra index. But I mean, we can step through it. So we establish our return variable. We create a map that we're going to use to store the kind of the inverse of our array. Our left pointer is equal to the first index. Right pointer is equal to the end index. We take the sum of that. Then we check if the target minus our current sum exists as a key in our map. If it does, then it contains the value of the index that completes the solution. Otherwise, we need to add, if it's too high, we add the kind of the right pointer to that map. And we decrement right and we repeat the process again. But now we have a new number in our map. So upon finding the next one, we can check again and just sort of repeat that process. So I like to think of patterns as like a skeleton upon which to solve a problem. There's a lot of details, and each pattern will sort of give you variables to tweak to match your specific case. But whether we're looking for a single sum pair or finding all the triplets, a lot of this code is the same. A lot of it is shared between the previous solutions. We're creating our start and end pointers. We're testing the predicate. Now we're incrementing or decrementing one of our 2 pointers.
I'm not sure I agree with your solution, but. I mean,
Cool. What would you do differently?
Well, I mean, just going through your solution, if, let's say we're on the ends, right? We got -3 and 3.
Right.
Equal to 0. Sums it equal to 0. K is equal to 0, so K 0 minus 0 is 0. So we're looking for index of 0 in a map that's found. First thing you're doing is you're incrementing and decrementing both. You're coming from -3 and 3 to -2 and 2. Well, what happened to -3, 2, and 1?
To -3, 2, and 1? That's a good point. That's an oversight.
You have to check all the pairs, right?
Yeah.
That's n squared.
Yeah, exactly. So we'd have to manage our incrementing and decrementing a little differently. Thanks for pointing that out.
Or maybe just do the map first and then do the left and right.
You mean step all the way through, or
No,
put the value in?
like step all the way through, create the map first, so you can have all the values there,
Right.
and then do the left and right and look for the difference. And
Yeah.
it's still open.
Yeah, there's a lot of ways to, again, like, you know, we have a kind of a foundation for figuring this problem out. You know, the challenge that's left once we know what problem we're trying to solve is how do we align those variables appropriately to fit that. There's a bunch of these types of 2 pointers problems on LeetCode, so you can check those out for all sorts of more practice. What's kind of cool, that rightmost column has to do with frequency of appearance reported in actual real-life interviews. So there's a 3-sum problem, and its frequency is very high, as you can see. So definitely relevant stuff. On to pattern 2, sliding window. So the idea here is we're going to dynamically decrement the end and increment the start of a. Actually, we're going to dynamically increment both the start and the end of a subsequence. So before we start at the ends and start to move in, here we're going to start at the beginning and move out. So let's look at look a little more detail. The general idea is start with 2 pointers or index variables to the start of your sequence. Increment the end variable, the second pointer, until some condition is met. Process values as you go. When the condition is met, add it to a result set. Remove the start value and increment start. And so I know there's a lot of steps in there, but it will make sense in just a moment. Generally, when you're dealing with these sorts of problems, you have an ordered container. You need to find some specific type of subsequence. Brute force squared is available, so you can rewrite a nested loop as a single loop. Let's take a look at a problem and think about it in terms of brute force. So given a sorted array of ints, return an array of sums of every kth subsequence. Here we have 1 through 10. Our kth subsequence is 5, so we want to return a sum of each kind of subsequence of 5 going forward, which in this case gives us 15, 20, 25, 30, etc. So we can imagine what a brute force would look like. You have your first for loop, you start, you have a second for loop, and then you go until you've met your kth subsequence requirement. You add that sum to the result set, and you move on. It's a lot of work.
How did you get the output again? You take, since k is 5, then how are we getting 15 and 20?
Oh, it's one plus two.
1 plus 2 plus 3 plus 4 plus 5, 2 plus 3 plus 4 plus 5 plus 6.
Oh, okay.
Yeah, so forth and so on.
Oh, so you're literally taking 5 and moving it every time.
Right.
Okay, that's a sliding window.
And there's a sliding window. Unfortunately, I didn't match the input array, but I think you guys can figure it out. So in our first our first iteration, our window is on here 0 through 4, and then 1 through 5, and then 2 through 6. As we're doing this, is there something conceptually we can take advantage of?
Yep. The numbers you've already met.
Exactly, right? So the idea, the insight is not to process the same numbers twice. Anyone tell me how to do that?
Just you subtract like the one that you're leaving.
I'm getting like airplane hand signals from the tarmac over there. You cut it out and then you move it in.
Pretty much.
Yeah, that's pretty much it. So we can take a quick look at a solution. I don't know why my quick find is totally broken in presenter mode. That's just awful to read, isn't it? Okay. So, sum solution kind of looks similar to the last one. We start off by naming our two, kind of the start and end of our window. Or actually, we don't. Apologies. We start off with our start and our sum. Start is set to 0. We then begin to loop, but we use our end as the index variable for our for loop, and we proceed through that for loop kind of in a normal fashion. And since here we're summing until k, once end equals, once n gets that many points out, k points out, or in this case, k minus 1 points out, we take the sum that we've been creating as we step through, we add it to our result array, then importantly, we have to take out that first value that we've already, that's no longer a part of the window from the sum value, and then move that start along. So what we're left with is in our next window, we're left with all of the values. The only value that we actually need now is 5, which is also where end has ended up at that point. So we can also visualize this one. Sorry for the shenanigans with presentation mode. Okay, so the first, 5 steps, we're building that window. Remember that condition while, if end is equal to k minus 1 or greater than or equal to k minus 1, then we would actually identify that we've expanded the window to the size that we need at that point. And from there, we're just sliding it to the end. So we don't need 2 for loops, we just need the 1.
Seems like an optimization would be if you actually use 2 for loops that aren't nested, but then you go from like the beginning to k, and you build the initial sum, and then you just go from k to the end. That way you don't have to have the check for if end is greater than or equal to k minus 1 every time. You avoid an if statement in the loop.
Sure, but we would need to do something new there.
Yeah, you'd have to you'd have one loop that just goes from 0 to k.
Right.
It builds the initial sum, and then you'd have the next loop starts where start is at 0 and k is at, or end is at k or whatever.
Yeah.
And you go from then. You
That
just
could work.
shift it back.
Definitely works.
Remove the if statement.
Yeah, one of these patterns is like, it's kind of the last one. I don't think we'll have time for it at this point, but there's like 4 ways that you could actually approach solving it but the mechanics of the pattern are really what's kind of the most, I guess, useful. So a second question. Given a string, I wanted to not use numbers, find the longest substring with no more than k distinct characters. So in this example, we're given our k distinct being 2. So we're looking for the longest substring in here where there only exists 2 unique or 2 distinct characters. Can anyone think of like a difference between this one and the last one in terms of how we might need to move our window?
Wait, does the output need to be in order? Because there's not, I'm thinking like a sliding window, like I'm thinking that.
That output is wrong.
It would only be EF instead of, yeah.
It would actually go all the way up to
Like-
the entire. It goes all the way up to the last f.
Last E, yeah.
Yeah, all the E, E, F, 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 E.
So it'll be EF, I think is the answer.
Yeah.
EF. Thank you for laughing.
I'm sorry, it says no more than k distinct characters.
Right.
So.
So
it's
2.
Less than or equal to. Okay.
No more than 2. Yeah, so I mean, you can interpret it as
If that's
1.
the case, then it would go up to the. Yeah, exactly. Then we would just cut off the fe at the end.
No,
Hmm.
No?
because that
Or-
still only contains E and F, right?
Yeah, then the total, I mean, yeah, the total number of different characters is still 2 because there's just E and F. It could be EF, 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 EF. It'd still only be 2.
Oh, I'm sorry. Yeah, I see. Okay.
If you ended it with F, it'll still be included in the output.
Yeah, we could make this output be the correct answer by changing the input, which I guess you could do for anything. If you can do that, do it. Much easier. So we can take a look at our window here. I think there might be a step or 2 missing, but essentially our first stop is AARR. We have no more, well, we've hit 2 distinct characters. So kind of the difference with before we were stepping up by 1 because we had that list of numbers. Here there's 2 A's, so it doesn't do any good just to move up by 1. We're still going to have that A, but we've moved end, and now our whole thing is invalid. So we have to skip ahead by the number of occurrences of that initial distinct value. This is a simplified example. Of course, if you had a sort of with this EEF and then you had more, you'd have to account for skipping when your secondly found distinct character was nested inside of the initially found distinct character. A little more complicated, but kind of takes away from the pattern. Anywho, we can kind of continue to move down identifying substrings with no more than 2 distinct characters. We can take a look at that, and the rest of it. There's one additional thing that needs to be done that we haven't talked about here, but we'll see that in code.
What's interesting here is that the window was bigger and then it shrunk and then it became bigger again.
Yeah.
So,
Yeah, because so in terms of achieving a valid window, and that first example, like once we built our window, because it was size-based, we could just worry about sliding it down. This is more of I guess the predicate for what a valid window is. It's a little more complicated, so we can have windows of varying sizes. that is not it. Okay, this is a horrible function named longest substring k distinct solution. So here, similar to the third problem from the last pattern, what we have to sort of add to this pattern is really the accounting. We have to keep track of two things. We have to keep track of the total number of distincts we've encountered so far. We also have to keep track of how many of them we've seen. So we can build a map called frequency or frequencies, which stores a given character and count its occurrences as we step through iteration here. This is a for range. We get an index and then we get the value at that index as we iterate through. We increment the frequency. If it's 1 after we've incremented it, then we've seen a new character. We move on to our test the predicate. This is kind of hideous looking, but essentially it's we're looking for our distinct count equals the k that we can't have any more of, and that we're either at the end of the array or the next value introduces a new distinct character, so we know that we stop. We've expanded the window. We've maximum distincts, we're at the end of the array, or the next one is a new distinct one, which would then invalidate the window.
What is rune here?
Rune is like Go's character.
Okay.
Yeah. So I don't know if this is going to be too helpful. In the hour before the meetup, we wrote some examples in Java for fun. So if that helps, target some, here's a different one. We can show that, I think we did a Java example an hour before this, which is always a great thing to do publicly.
What was his question?
What a rune is. And the rune is a character,
Oh.
essentially. Yeah. It is kind of gross. Yeah. So just a few different, I guess the idea though is exactly the same. We keep track of the number of distincts we've seen. We have the start of our window declared here. It's I, but it could be n in that for loop. We have the same test, and then we handle that in the same way. Of course, the sort of tricky bit here, and gets more complicated in other, maybe a more real-world solution, or real-world problem, is you have to then also account for the fact that you found a window, just like as we were keeping track of the distincts and the frequencies. We have to update the frequency count, but we have to update the number of distincts we've seen, and then we also have to move ahead our start by the number that is held in that frequency range. So in the, if we're going from the first window to the second window, from AARR to RRBB, we have to jump ahead to 2 spots, not just the 1. So, pattern, logic the same, specifics modified for the specific problem at hand.
If your given input had 2 EEFFFEs in the sequence, but at different places, would it find the second one?
Would it be within that last window?
Let's say that it was a longer input.
Right.
So you had 2 instances of the output that had the longest.
Sure.
Or even 3. You might even have the last one have an extra E at the end so that it beats the other ones before it.
Right. And that would be the longest, because we're also comparing back to a maximum, keeping track of that.
Okay.
Yeah. So when I was thinking of this problem, it's like, what do I have to keep track of here? What do I need to know in order to move my window around? How do I know what I've found? The frequency of each character seen thus far, how many distincts I've seen thus far, and what my max is. But the underlying logic is very, very much the same. This exact question was actually sent to me today by him. I He found this on LeetCode, Amazon online assessment, most common word and substring with K distinct characters. So apparently that's actually out there. The anecdote from the 2 pointers problem, I was actually in an interview with a big tech company, and they asked me the first question, I was like, oh, 2 pointers. And then they asked me the second question after that, I was like, oh, 2 pointers again. So, very, can be very common. And it's up to you to decide, have I seen this before? And then I guess this close that. Interesting problem. Thank you for sharing it.
Do 2 pointers always start on the left and the right? Is that, and then Windows starts from 0?
Correct. Yeah. Yeah, the window we're expanding to make one and then moving it, the 2 pointers kind of starts at the beginning and the end and moves in. So this is for you guys. This is the last problem for tonight for this pattern type. Given the string, find the longest substring with only unique characters. I'm pretty positive it's free of typographical errors here, so that's awesome.
Good job.
Thank you. So the input string, I'm not going to read that. The output string, it's on the monitors. You can test with any string you want, but let's do 10 minutes, as we did before, and then discuss possible solutions afterwards. I can blow through this. Yeah. I can do it quickly. It's the easiest thing. Just hit that. Let's go.
Oh, that's on 6, yeah.
So what do you think? You want to become a software developer? Okay. She says that, and she's like, look at my spreadsheet. I'm like, oh, God, it's so big and complicated.
Yeah, I got my CSV deck.
Every time you say counting, I'm like,
several days and then dropped it. So I started out in mechanical engineering.
Should be in like the description.
That's not one. Yeah. That's a common story. It's a common thing. My friends dropped out. But everything was started.
Yes. And I'll probably ask you for an email or something.
Yeah, I was like terrified of calculus, and he explained, he's like, no, it's way easier than algebra. And when he explained like f of x function, it just made sense, you know. So it's like I think it's about like which is the same thing with coding. Like you can have like entire chapters in something like an ancient Arabic versus somebody just explaining it in one way in one sentence.
I want to say I'm so thrilled that you decided to live code all of this. Why? What's the reason? Well, first my editor is like working out. I should have used the band, like I always do. But I thought like, oh, presentation. Ben is the best editor ever made by anybody.
This is the most nectarine one.
No, it's the best. You can stop there. It's the best, period. Way better than Emacs.
I guess it says
It's a good call. Yeah, and most a lot of comments, but
it's
I
for,
said wanted to do.
Question.
yeah, for,
Yeah.
So you guys have plans to do it in a bunch of different languages?
Oh, we can try to go to, hey,
It's really
Oh,
just
yeah,
like
so like,
whatever
because I think we're going,
glad that I brought it up last second.
So then the next one is when you do K, and then you're keeping track of all of these, and then once you here.
Oh, they gave you guys cards?
Yeah.
So then you just be able to use the kitchen.
Yeah. Yeah, you got the full tornado facility.
Let's see.
You also probably the card will have access to. Actually, you should ask them if you have access to the gym,
Oh, I didn't mention that.
because then you would also have access to the rooftop pool that's on the other side. Which is pretty good.
No, that wasn't part of the tour. Rooftop pool. Is that like from hackers getting messed up?
No, it's a
Okay.
okay.
Was that a thing like a pool on the
I
top
had
of the
access.
pool?
I had access to it.
Oh, okay.
Yeah. Windows are 6, now that you hit 7, it's bigger.
I'm here at the address.
What if you don't, what if you don't slow down? For example, LAKDJF, if you have the same length twice, you don't have like, do you remember when I assumed that there's one?
Make it happen, right? If you wanted to. If there's only one, then you'll return the one. If there's more, then you'll return those. So instead of breaking what you found, it you just have like a results set. You know, you can have an array of strings and you just append that each one on and at the end.
Python has this.
Right.
So you can just like inserting it. So you know, something that
Right, and then you would take the length of your set, and then you could say, okay, how big is this, and then keep going and see what's bigger. Of course, though, like, so the LAKD, you might not want to throw away all those numbers now. So if you look at like, yeah, all those values, because first,
yeah, I have it.
I mean, you can imagine like a really long string, right? So, where do we enter first? LAKDJFL, right? So, but part of our answer includes the KDJF, right? So we have to keep that.
Makes sense, yeah. If I could just.
Is it making sense?
Yeah, it is. And how do I get to this back to you?
It's on the meetup homepage. Oh, I can email the link out soon. But it's on, I think it's on the description.
Yeah, there's a.
Yeah.
Maybe they have like, it's like a soda test.
Just making sure it works right now.
Smoking room.
You need,
Specific to that.
like you've used Slack multiple
Yeah,
weeks, right? So you need a.
Yeah, like each
So much more like girthy than other buildings.
Say okay, it's coming email back.
I always like
Oh, right.
Co-parentry, we talked to Ben about making a relationship with Ben for historical preservation. But I forgot how impressive that is. It's really incredible. And there's, it's really cool how extensive the underground
Yeah,
passageways are.
I love those. When I was an intern there, which was weird. But how's everyone feeling about this one? You're not feeling good? Okay. Anyone feeling good about this one? Yeah, we got one. Sweet. Okay. Anyone want to share their idea of a solution? No takers. Great. So this one is actually a little simpler than the previous one. As we're sliding through, you know, the question here is, when do we move up start? And then moving along end. So we can take a look at one implementation of this idea. So here's our longest unique substring. We're keeping track of our indexes in a character index map. Where instead of doing, actually, no, we are doing start and end. So start is 0, end is our I. We're keeping track of longest as we step through. This should sound like I'm repeating myself because I kind of am, and that's the whole idea. We do that check with the map. The whole idea of the map is just keeping track of if we've seen this before. There's probably other ways to do that. We take a look at our current substring, right? So we're looking for a predicate to tell us that we're done. We compare through each step. If it's the longest, then we assign that. When we're done, we just return our longest. Of course, you could modify this to return multiple strings of equivalent length or whatnot for your specific problem.
Realize that longest was actually a string.
There's a joke about Go, I'll tell you, not here, but after. I heard at a conference once. I think we threw this together in Java in like a few minutes before this meetup. It's actually shorter. When Java is less verbose than another language, that tells you something. If only Go had generics. Right. So same idea. We keep track of our longest. Our start is 0. We iterate through. We do our accounting just a little bit differently. Otherwise, we test this. We test the substring all the same. Let's see. I'm checking what time it is. So we have a hard stop at 8. We have 12 minutes left. So I'm not going to go fully into the next stuff, but I will preview it. If you want more practice with sliding windows, again, LeetCode, sliding windows, it's a whole category. I drew a blue arrow to that line because that frequency was the maximum for being seen in a real life interview, and it's longest substring without repeating characters. Sounds a lot like what we just did. So the third pattern is fast and slow pointers. Do you guys want me to dig into this real quick, or do you want to break here? Yeah. Okay, cool. This is probably, at least in my mind, just one of my favorites of the ones tonight because I like linked lists. Fast and slow pointers. Use 2 pointers, I feel like I've said that before, which move through some sequential data structure at different speeds while never evaluating the same index twice. Sounds a little like the last one. So the classic example for this is detecting a cycle in a linked list. Anyone not familiar with linked lists? Okay. So an array, each element is kind of ordered contiguously. Each kind of index is right next to the other one, and that's how they're kind of connected to each other. In a linked list, each sort of node has its value, and in a single linked list, it has a property called next. And that next property is the location of the next node down. So we have our, where it says head, which is the start of our linked list, we have 1. That 1 node also knows where 2 is, and 2 knows where 3 is, and 3 knows where 4 is, and that's how we can iterate through this. We can keep calling .next to get the next node, and then to continue down. We have a cycle, so normally in a non-cyclic linked list, our last pointer there at 6 would be null, or maybe the one it points to is null. So when you call .next, you get null or nil or whatever your language supports, and you're done. In this case, though, when we ask the 6th node, hey, what's next? It says 3. And if you just keep .nexting, you're going to be nexting forever. So that is a linked list cycle. Any questions on what a linked list cycle is? Sweet. What's fun about this is I found an article called The Worst Programming Interview Question Ever. And it uses words like completely inappropriate. And it says, this question perfectly represents everything that can go wrong in an interview. And then there's a lot more vitriol. And then the contents, the part that's below the screen says it's completely disconnected from reality. I'm not saying I agree or disagree with that. It's up to you to decide. But it's talking about detecting a cycle in a linked list. So let's do that. Let's see how awful it is. Problem 1, given a linked list, determine if a cycle exists. The head here, the input-output is almost useless. But, so given a list, find the cycle. So let's do this after that. Anyone have any ideas first?
2 pointers, one keeps going twice the speed of the first one. They intersect
That's exactly right. Exactly. So
Nailed it.
nailed it. All right, we're done. Go.
Does this tell you where they intersect though?
It doesn't tell us where, but the problem number 2 is tell us how long that intersection is. So you can figure that out with its length. But in this case, we're just saying, tell me true or false if it's there.
Does if a linked list is pointed to it, let's say it's one node and it points to itself, does that count as a cycle?
That's very philosophical.
Because the next
Dot
pointer-
next me,
the
dot
next-
next me. Yeah, I guess
the
it
next-
is.
Me.
It's
Yeah.
me. Just talking about me.
Yes.
Me.
It's all about.
So fast is dot next. So yeah, I mean immediately be like true on your first iteration. That is like very. I enjoyed that question. Thank you. A node of one node next thing. How do I get out of this? Okay. Why do I not have? I swear this editor was working like earlier today.
Because you're presenting, it's not one.
Just waited for that right time. Come on, there we go. Oh, there we are. I swear I wrote these. Okay, detect a cycle exactly as you described. This is a really simplified, linked list we're dealing with. We're just dealing with the nodes. Fast and slow both equal the node that we're given. While fast does not equal nil and fast dot next does not equal nil, do this loop, right? If it's nil, then we know that we do not have a cycle. Next, slow dot next equals, slow is the next one. Fast is the one after that. It's moving, slow is going 1 by 1, 1 by 1. Fast is going 2 by 2, 2 by 2, 2 by 2. The very simple predicate, so if slow equals fast, then true, we have found our cycle. If we've hit we've hit a nil, then we know that we're done. We know there is no cycle.
In the case of the one node, it'd be slow is me, and then fast is
Still you.
still you.
Yeah, it's all, if you start off on you and you next back to you, and then you start off on you and you next back to you, and then you next back to you, you're still on you. A lot of you. Okay. So problem number 2, given a linked list, if a cycle exists, return its length. Hint, small variation on the first solution.
Keep the first pointer at the intersection and just count the.
Exactly. And what?
And you just keep, you move the other pointer and you count the number of turns it took to.
Exactly. So essentially, I just like to leave, since slow is already going 1 by 1, fast stops. So we've hit our case. We've detected our cycle. Now we're just going to keep track of how many times we've seen it. We're going to leave fast where it is. It's not going to move, and we're just going to do slow dot next dot next dot next until they meet again, giving us our length. Very good.
Can you not do it without, once you find it?
Sorry?
Surely you can keep count of how many steps you've taken and how many the slow pointer has moved.
Sure.
So you don't
Yeah.
have to keep going after you find it.
You could do that from the onset.
Yeah,
Sure.
that's possible. Okay.
Yeah. All right, the last question for this one is find the middle node. Now we could take time here, but if anyone has a solution, just let me know. Find the middle node of a linked list.
Can we use extra space?
Sorry?
Extra space?
No.
Can you just do the same exact thing?
Yeah.
When the first one gets to the end, or the fast one gets to the end, then the middle one,
Exactly.
so it's the middle.
Yeah. So when we're looking for the middle of a linked list, slow is moving 1 by 1, fast is moving 2 by 2. So let's say we have 10 elements in our linked list. 1 and 2, 2 and 4, 3 and 6, 4 and 8, 5 and 10. So if we have a middle node, that's where slow is. When fast hits the end, slow is at the middle.
That's if you have an even number
So in your check though, you could be checking is fast.next nil and is fast.next.next nil, and then you could handle that off by one accounting there. But that's key observation, or else it would be wrong, or could be. So I've been repeating myself a lot. Meta pattern, 2 references into a thing is useful. So maybe it's not necessarily having to keep, is this 2 pointers, or is this fast and slow, or is this sliding window in your head? Well, looking at a problem, maybe it's like, if I take 2 references, 2 indexes, 2 pointers into this data structure, can I use that in some way? Can that help me? Maybe it's a window, maybe it's one of the others. So I think that's my big, at least, insight from that is two references are super useful. There's a bunch more. I sort of anticipated that we were gonna, each pattern kind of takes a while. Merge intervals would be up maybe in a future session. I'd love to hear your feedback. You can drop it to me on an email or on Slack, or if you want to just grab me after this and say, hey, that was terrible, that was good, I want to know more, I want to know less, hopefully not less, let me know. Otherwise, I'll be hanging out here for a little while. If you have any questions, you can feel free to ask, just talk.
Did you say you would include both the slides and your code, even though would you include the code as well as the slides?
Yeah, after a little bit. So some of it was written like very quickly today, and so I got to clean up that repository. But yeah, that will be going up within probably this week. All right. Thank you. Next month, George, so please come back. We'll be in the other room across the hall, desks for everybody. And thanks so much for coming out. Fill it out. Thank you.
Thank you.
Bring your laptops.
Now exercises for the people in the class.
Thank you for coming. Wow.
Yeah, I mean, that's kind of the point of the exercise. Oh, it's done.
Can I go there later?
Probably just announce it in general. Yeah.